Okay, so Gary will start.
So thank you, Dieter. Thank you, Miguel, Irina, and Kungun for having us here. In this talk, Lars and I would like to tell you about our work last year, as well as two ongoing works with a bigger cast that includes Alex Goh, Edward Morgan, Jan-Peter van der Schaar, and Vasa Sivisma. So let me start with some motivation. So a lot has been conjectured about de Sitter space and inflation in quantum gravity. Now, if I try to list all the papers here, this page will be filled up, and I'm afraid I will miss someone. So consider yourself prominently cited whenever I mention the ideas. These conjectures take different forms, such as the refined de Sitter conjecture, the transpumpkin censorship conjecture, the no eternal inflation principle, and the censorship of quantum break time. So as a result, various timescales have been suggested as the lifetime of de Sitter space, ranging from a few Hubble times to the scrambling time to the page time. So the question that we would like to address is whether we can use ideas in quantum information theory to put bounds in the lifetime of de Sitter space and the inflation. Now, this is a potentially promising avenue. Thinking about information recovery for black holes have led to several paradoxes. These paradoxes are useful because they can teach us when effective field theories break down in quantum gravitational systems. This is, of course, very much in the spirit of the Swampland. So shock waves and entanglement entropies have been useful tools for learning about microscopically how information gets transferred and recovered for black holes. We will see how we can use them to study de Sitter space. So one may also wonder whether the recently discovered island contributions for black holes can play a role in de Sitter space. So this is an outline of our talk. I will start off with a discussion of shock waves in de Sitter space and talk about information bounds. Then Lars will tell you about the vacuum state of what he called a curious observer and discuss island contributions in de Sitter space. So let's start with shock waves and chaos. So in both our presentations, we will mostly work in the static patch of de Sitter space. So the static patch describes the experience of an observer sitting at the pole. For example, we have Bob here sitting at the South Pole. Now, de Sitter space has an entropy proportional to the horizon area and a temperature that is set by the de Sitter scale, the de Sitter radius. This is the metric of de Sitter space in static coordinates. And for simplicity, we consider three-dimensional de Sitter space because, as you will see, much of the action is in the time and the radial direction. So in these coordinates, the poles are located at the origin, r equals to 0, whereas the past and the future horizon corresponds to r equals to L that are denoted by these diagonal lines. So since the entropy of de Sitter space is finite, its microscopic description should involve only a finite number of microstates. Therefore, we expect we would encounter an obstruction when we try to assess more information than the de Sitter entropy. So we would describe two thought experiments that probes the de Sitter entropy. And as you'll see, these entropy considerations suggest bounds in the lifetime of de Sitter. The first experiment involves shock waves. So consider a static observer that emits some small amount of energy, E naught. This energy is exponentially blue shift when measured at a later time. So it's appropriate to think of it as a shock wave. So as we'll see, the back reacted geometry, taking into account the shock waves effects, can be described using this global light cone coordinates. So in these coordinates, the past and the future horizon corresponds to x minus and x plus equal to 0. And the metric for empty de Sitter space take this form. Now, the back-reacted solution is simple in the infinite boost limit. In this limit, the shock waves travels along the path horizon with E naught its energy when it crosses the origin. So this is the stress tensor for the shock wave. If the stress tensor of this shock wave satisfies the null energy condition, this parameter alpha that appears in the metric is positive. So a geodesic crossing this shock wave would experience a time advance because of this shock wave contribution. Now, this time advance is not in violation of causality because the asymptotic causal structure of the de Sitter space is different from that of flat space. This point was explained or proven mathematically more rigorously by Gao and Ward, but intuitively we can understand this. Sending positive energy shock wave out of the static patch slows down the expansion, making it possible for a message to go from one pole to the other. And indeed, by a coordinate transformation, we can understand this time advance in terms of a traversable wormholes connecting the two static patches. So the question is, how much information can we recover and how long does it take? Now, the information recovery time is bounded from below by the time it takes for the horizon to absorb a qubit. This is known as the scrambling time. And this time scale can be deduced from a 4-point function known as the out of time order correlator, or Otop in short. So the out of time order correlator measures the sensitivity of an operator, let's say V, to some initial perturbations W, which can be generated, for instance, by a shock wave. So for black holes, the Otop was found to be exponentially sensitive to the initial perturbations. The exponent here, known as the Lyapunov exponent, saturates the chaos bound. So black holes are fast scrambling. What that means is black holes scramble information as quickly as theoretically possible. Now, the time scale for the Otop to change by 1 is known as the scrambling time. And you can see that this is given by the infrared scale of the problem, the de Sitter scale, times log of the de Sitter entropy. So we can do a similar calculation for de Sitter space and see whether the de Sitter horizon is also saturating the chaos bound. So like for black holes, the Otop quantifies the chaotic behavior of the de Sitter horizon. The Otop can be thought of as a scattering amplitude, and it's given by the overlap between an in state and an out state. So the in state and the out states are created by perturbing the vacuum by these two operators V and W. The difference between the in state and the out state is the time at which these operators are inserted. And the vacuum on which these operators act is the Bunch-Davis vacuum, which is the thermal field double states that maximally entangle the two static patches. Now, in general, the Otop is a rather complicated object, and we could not obtain analytic results. However, for conformally coupled fields, we can compute the Otop analytically. And the Otop, in this case, can be expressed in terms of some special functions, some hypergeometric functions. And when expanded, displays an exponential sensitivity to the initial perturbations. So like for black holes, the exponent here saturates the chaos bound. So black holes are also, de Sitter space is also a fast scrambler. So the time scale for the Otop to change by 1 is the scrambling time. In this case, it's given by log of the de Sitter entropy. So I should say that de Sitter space was conjectured to be a fast scrambler by Susskind, but it was not until this work with Lars and a subsequent work by Blumert that this maximally chaotic behavior of de Sitter horizon is explicitly established. So to see that the scrambling time is the recovery time for information, we could consider the following thought experiment. So the Bunch-Davis vacuum maximally entangled the two static patches, and the Hamiltonian constraints require the shock waves to be sent symmetrically from the poles. So whenever Bob sends a message, shock waves from the South Pole, there should be another shock wave sending out from the North Pole. And you could ask, how, in the presence of these shock waves, how long does it take for a message from the North Pole to reach the South Pole? Or if you want to stay on only one side, how long does it take for a message for the South Poles to return? So Bob is our static observer, and let's say Bob waits for n evos after Alice sends her message to emit a shock wave. So Bob has only access to Hawking radiation, so the maximum energy of the shock wave that he could generate is n times the thermal de Sitter energy. So the time it takes for the message to be recovered is given by the time that Bob has waited, plus the time when the message returns. And so you can see that the time for information recovery depends on the shockwave energy that is parameterized by n. So extremizing over n gives the shortest time for the information to be recovered. And indeed, this is given by the scrambling time. You could also ask, how long does it take? You could also ask how many bits of information can be recovered. The size of the wormhole is set by the energy of the shockwave. The bigger the shockwave energy, the bigger the size of the wormhole, the bigger the value of alpha. And if there are n bits of information in a message, each carrying an energy E bit, the total energy of the message should be smaller than the shockwave energy in order for us to ignore back reaction. At the same time, the energy of each bit has to be big enough to fit through the wormhole. So combining these constraints, we find that the number of bits that we could recover depends on the shockwave energy and is bounded from above by the de Sitter entropy. So if more than S de Sitter bits of information are transferred, back reactions becomes large for sure. And we could ask, how long can this experiment last? The smallest energy of the shock wave is the de Sitter thermal energy. In this case, we can send at most one bit of information, and the information recovery time is given by the scrambling time. This is the minimum time that we found before by extremizing the number of evos or extremizing the shockwave energy. The highest energy shockwave has a Planckian energy, and with such high energy shockwave, the wormhole is big enough for up to S de Sitter bits of information to be transferred, and the information recovery time is the page time. So in this thought experiment, the back reaction becomes large when we reach the page time. You can think of the page time as a conservative estimate for how long a semi-classical description of de Sitter space can last. When we wait for S de Sitter evos before sending the message, when Bob waits for that long, he has collected so much radiation that a black hole would form. And semi-classical gravity may break down even before that, as you see in the second thought experiments that Lars will tell you about. So let me just hand this over to Lars now.
Okay, let me just go to full screen mode. All right, you can see my slides, right? All right, very good.
Yes.
Yes, so in the second part of the talk, I will continue where Gary left off. And that's indeed so what I will do, is I will describe a sort of second thought experiment, also involving a static patch observer, that wants to know what's happening beyond the horizon. So that observer wants to collect some radiation and perhaps reconstruct some information from beyond the horizon. But instead of using shock waves, we will talk about entanglement entropy. And this analysis is very much inspired by some recent developments in the black hole information paradox. So let me first briefly review that. The black hole information paradox arises as follows. So let's say that we're given some black hole that is radiating. And what we can do is we can compute the entropy associated to this radiation. This is a computation that was, for example, done by Hawking. And what you find is that the entropy of the radiation scales linearly with the time, and it increases. And so it keeps increasing without bound until you completely evaporated the black hole. However, we also noted at the same time that the black hole also has an entropy that is measured by the Bekenstein-Hawking formula. And because the area of the black hole is decreasing while it's evaporating, that entropy goes down. Now, the paradox arises is when we think about this black hole evaporation process as being described by unitary evolution. Because if this process is unitary, then it cannot be the case that the thermodynamic entropy exceeds the black hole entropy. And this was nicely explained in a very famous paper by Page. And he, under some very reasonable assumptions, showed that if black hole evaporation is a unitary process, then the entropy of the radiation should follow the green curve. So it should initially increase until some time, which we now call the Page time, and then it should decrease back to zero until the black hole has completely evaporated. So then the question is, what type of corrections are we missing when we're doing Hawking's computation such that you get a unitary Page curve? And this question is very swampy in nature because the breakdown of the effective field theory describing the radiation entropy here, that happens at a point where curvatures are still very low. So it's not normally a place where you would expect, let's say, quantum gravity corrections to be important. And so recently, over roughly the last 2 years, there have been a series of papers that have made this question more sharp. And in some particular models, they have understood exactly what are the corrections that were missing. And by doing so, they have computed a unitary Page curve for evaporating black holes. So there's like lots of interesting work. So here I give you a subset of the references. And so what the sort of key insight was into answering this question is that if you want to compute the entropy of an evaporating black hole, so let's say that here I draw the Penrose diagram of an evaporating black hole. There's some radiation, and you can compute the entanglement entropy of that radiation on some space-like slice sigma radiation. And the key insight has been that if you want to compute this radiation entropy, that you should allow for possible contributions known as island contributions that are given by disconnected regions with respect to the radiation slice, and that can give a contribution to the radiation entropy. So the formula, which we call the island formula, is given as follows. So let's say that I want to compute the fine-grained entropy of the radiation entropy. Then what I should do, I should allow for a contribution of an island region, which has an endpoint x. I should compute the area of that region divided by 4g. And I should add to that the von Neumann entropy of the union of this radiation slice and the so-called island slice. And then finally, the final step in order to compute this radiation entropy is that I should extremise over all possible islands until I find what is known as a quantum extremal surface. And then if there are multiple options, then I should take the one that gives you the lowest entropy. So the way I explained it to you now is may seem a bit ad hoc, but by now there's very good evidence that this is indeed a correct formula. And you can also derive it using Euclidean path integral techniques. So then by taking this formula and applying this to the evaporating black hole, there are two possible islands that contribute. So at early times, you find that a so-called trivial island dominates. So what that means is that you can always allow for the possibility where this blue region shrinks all the way to zero, such that the radiation entropy is just given by the von Neumann entropy of the radiation slice. And then what you find is the increasing orange line, so the Hawking curve. However, then if you wait for a while and the black hole has evaporated for a sufficient amount of time, what you find is that a non-trivial island can contribute. So it's an island as drawn in this figure. And then when you compute the radiation entropy using the non-trivial island, you find that the dominant contribution is given by the area of the black hole. So this island lies close to the black hole horizon. So you find that this is an entropy that is decreasing because the area of the black hole is going down. So when you combine these two contributions and you take the minimum value of both possibilities, then indeed you find the Page curve. So you initially find that the entropy goes up, but after a while, the island kicks in and it goes down. Okay, so that has been a very interesting and successful story. And now we want to know if we can talk about something similar happening in the Sitter space. Is there a similar breakdown of effective field theory when we consider the entanglement entropy in the Sitter space? And this is maybe not so surprising if this would be the case, because we know that the black hole horizon, just like the Sitter horizon, is thermal. If we take a static patch observer, then we can ask the question, let's say that I throw some information behind the horizon, as we saw in the first part of the talk, then will I be able to reconstruct that also from an entanglement entropy perspective? So this is an interesting question, but there's one sort of key difficulty in doing this as compared to the black hole case. Because for black holes, if you take a black hole in asymptotically flat space, what we can do is we can go to infinity and collect radiation there. And then we don't really need to worry about the back reaction of that radiation. However, if you take a static observer, that observer is sitting inside of a static patch at finite volume. So if you want to reconstruct some information by collecting radiation, then the only place for you to store that is inside of the static patch. But if you store some positive energy inside of a static patch, then that necessarily leads to some back reaction. So if you take some positive energy inside of a static patch, then the horizon will shrink a little bit. And you have to take this effect properly into account. So what this means is that you actually have to go away from the thermal equilibrium of the Banach-Davy state. And so in order to do this in an analytical way and keep track of the problem, we make use of Jackie-Teitelbaum gravity to compute this, where we can solve this back reaction problem analytically. So Jackie-Teitelbaum gravity looks as follows. So one way how it can arise is if we take a black hole in the Sitter space, and we take the black hole horizon to be close to the cosmological horizon, then if we take a near horizon limit, what we find is an ds2 times s2 geometry. And that can be appropriately described by Jackie-Teitelbaum gravity, which you then obtain as a dimensional reduction. So the action looks as follows. So we have a first piece, which is a topological term that is proportional to this constant phi 0. So that will be proportional to the de Sitter entropy. Then there is a second term which contains a dynamical piece. So it contains a dynamical dilaton that measures a deviation away from the Naghi limit. And finally, what we do is we couple this to a two-dimensional matter sector that is conformal and has a large central charge. So when you compute the equations of motion of this action and you look at a vacuum solution, so for a moment we set the matter sector to 0, what you find is a solution that is natural from a static patch perspective. So here I wrote the two-dimensional static patch in these coordinates. And then what you find is that there's a solution of the dilaton that goes as this cosine of theta, and it contains this constant. And as I promised, the de Sitter entropy is given by the sum of the constant part of the dilaton and the dynamical piece. So then if you draw the Penrose diagram, so in 2 dimensions, the de Sitter Penrose diagram is a rectangle. Then what you find is these 2 static patches. And I also indicated here regions where the dilaton becomes very large or very small. And that's important because in JT gravity, the dilaton measures the effective gravitational coupling. So regions where the dilaton is very large correspond to weak gravitational coupling. And the regions where the dilaton becomes very small correspond to strong gravitational coupling. So here, these regions that I colored red, those are typically interpreted as the remnants of the black hole singularity. They were there when you did the dimensional reduction from 4D to 2D. Okay, so then when you want to include matter, you can do that. And then we can solve the equations of motion in the presence of this matter. But then what we have to do is we have to pick a particular vacuum state for the matter sector to be in. And as Gary said in the beginning, we're interested in what I call the vacuum state of a curious observer. So that's this static patch observer that wants to collect radiation in order to possibly reconstruct information from beyond the horizon. So what this means is that we want to construct a state in which an observer is collecting the Hawking radiation that is coming from the horizon, but there is no radiation that is escaping from the static patch. So the way you can do that, so this is also a thermal state. So for a general thermal state in the static patch of the sitter, the stress tensor can be written down as follows. So we see that it's proportional to the central charge, and there are two inverse temperatures appearing here, corresponding respectively to the right moving sector and the left moving sector. So then what we're doing, if we, for example, would pick the Barnes-Davies states or a thermal equilibrium, then we take both temperatures to be equal and take them to be the sitter temperature. But if I want to construct this state in which radiation is absorbed instead of a static patch, then I take, in this case, the right moving radiation to take the sitter temperature, and the other sector I take to have 0 temperature. And importantly, this breaks the thermal equilibrium of the Barnes-Davies state, and this will lead to some back reaction effect. So what we have to do is we have to solve the equations of motion, or we have to solve for the back reaction. So if you do that, then you find that there is this following solution of the dilaton. So you might recognize this second term as the piece that was already there in the vacuum solution. And now if I include this meta contribution, then there are two additional terms that are appearing. And note in particular this logarithmic piece here, which contains an explicit time dependence. So this really tells us that indeed we have generated some time evolution and we broke the thermal equilibrium state. For the semi-classical approximation to be under control, we have to take the following hierarchy of all the constants. And then what you can do is you can look at the Penrose diagram again in this back reacted solution. Here I plot the piece that is relevant for us. So here we have again a static patch region. There's a region beyond the horizon. But now if you look at this dilaton solution, there's this additional place here where the dilaton becomes very large. So this is the region where gravity also becomes weak. And this will be important when we want to apply the island formula, because that only is valid when you apply it in a region where gravity is weak. And if you look at the stress tensor in Kruskal coordinates, you find that one of the sectors is 0, so that is the Barnes-Davies value, and the other value, the other sector is non-zero, and that will tell us that there is indeed a pileup of positive energy inside of the static patch. So now having done all that, we're now finally in a position that we can compute the fine grained entropy. So what we do is we specify a region R where radiation is collected and compute the entanglement entropy of that using the island formula. So what that means is that we should allow for a possible contribution of an island that is that I drew here. And then indeed what you find in this non-equilibrium vacuum state is when you extremize this, the island formula, you find that there is an island located close to the future horizon and that it evolves in the plus direction as follows, as described here. And then there's also the possibility, of course, that there's this trivial island, and indeed we find that at early times, there's this trivial island that dominates. So here you also see that the entanglement entropy of radiation in the static patch increases linearly with time. But then after a while, a non-trivial island develops, and that is just as the black hole case, that is proportional to the entropy of the horizon, which in JT gravity is given by the value of the dilaton, and that decreases. So when you take both contributions and you take the minimum, then indeed you find that initially the entropy increases, then there's the page time, and the island starts, the non-trivial island starts to give the lowest contribution to the entropy, and the fine-grained entropy goes down again. As you can express the page time in terms of the parameters of the model. So this curve looks very much similar to the evaporating black hole with an important difference. And that is that for the evaporating black hole, we could assemble the radiation at infinity, but here we are assembling radiation inside of the static patch. So you have to be careful that back reaction does not become large. So that's what we'll compute next. So we can sort of reformulate the question is, could it be, for example, the case that a singularity forms because we're collecting so much positive energy? And there's one complication, which is we cannot use a classical singularity theorem because the Hawking radiation violates the null energy condition. However, luckily for us, there are quantum singularity theorems that generalize this, the classical singularity theorems to situations where the null energy condition is violated. And using one of those, we can compute what happens. So roughly speaking, this quantum singularity theorem, what it tells you, if you take some Cauchy surface sigma, and there is a point P that splits it into two regions. then you can compute the generalized entropy of that point P. So that means that you take the area over 4G of P plus the von Neumann entropy of part of that Cauchy line. So you trace out the interior part. And then you can, what you can do is you can compute null derivatives in both directions, so in the plus and the minus direction. And then a quantum thread region is defined as follows. So it's a region where the generalized entropy of P is decreasing in both directions. And then the quantum singularity theorem roughly tells you that if there is a quantum thread region, that a singularity will form. So we have all the technology to do that and to compute the generalized entropy in our non-equilibrium state. And then indeed what you find is that a quantum thread region at some point develops. So when you when a static observer is collecting radiation for this amount of time, so which we call the trapped timescale, which I indicate here with this orange line here, then a quantum trapped region develops here. So if this observer crosses this line, then its fate is sealed and eventually it will hit the singularity in this quantum trapped region. So from that perspective, indeed, back reaction becomes large at this time scale. But then it's very interesting to compare this time scale with, for example, the page time or the scrambling time. And what you typically find that in the semi-classical regime, so where we trust these equations, you find that there's a parametric separation between these different time scales. So we have, for example, the Hubble time, we have the scrambling time, we have this trapped time scale where the singularity will form, and then finally we have this page time. And interestingly, the singularity already forms at the time scale that is parametrically much smaller than the page time. And this is actually something, so I didn't really have time to talk much about it, but the fact that this happens is actually necessary to avoid certain quantum no cloning paradoxes. So this result seems to be robust in that sense. But yeah, what the conclusion is that once this observer collects radiation for this amount of time, its fate is sealed and its life will end at the singularity, meaning indeed that back reaction already becomes large at this time scale. Okay, so that brings me to the conclusions. I'm slightly over time. So what we did is we considered two different experiments involving information recovering that probed the de Sitter entropy. So what we saw is that by using shock waves, it's possible to recover information, and back reaction is small for at most a page time, but possibly shorter. So then in the second part of the talk, I showed you how we can define a non-equilibrium vacuum state to find a page curve for the de Sitter radiation. However, because we are collecting radiation inside of a static patch, at some point back reaction will become very large. And you find that this happens at the time scale that is hierarchically smaller than the page time. So we all this analysis for the static patch observer. But of course, it would also be very interesting to try to understand a bit better if you can apply some of these ideas, for example, to an inflationary scenario. So that is something that we leave for future work. So thank you.
All right, thank you very much, Lars and Gary, for your very nice presentation. We have time for a few questions. So who wants to ask first? I see Kumron is raising hand.
Thank you for the nice talk, both of you guys, very beautiful. So I have to understand better, but your trap time was what in terms of the Hubble scale?
Yeah, so let's see. So let me go to the slide. So the Hubble scale in this case is just the Sitter length, of course, or 1 over the Sitter length, and this trap time scale, so it's written here. So phi s is the constant that appeared in the classical solution of the dilaton. So that measures the deviation away from the Nagai limit, and c is the central charge of the matter sector that we use.
But can you just say it in terms of is it not determined in terms of h, the Hubble parameter?
So it's always much bigger than h. So you can write it to these.
Is there something that you can say purely in terms of h?
No, so it will crucially depend, I think, on this deviation away from the Nagai limit, which I don't think has like an obvious relationship to the Hubble parameter.
I see. And the other question is that, so these will give you upper bounds to the lifetime of de Sitter, right? In other words, you're assuming that there is a de Sitter and so forth. What are the possible inconsistencies? And these would be the inconsistency. Whether or not there are other effects, yeah, exactly. this would not capture. So this would at best be an upper bound.
That's right.
And
Yeah,
so,
yeah,
so
I
it's
agree with that.
surprising, as you say, that the page time certainly is, people would have thought is an upper bound that you cannot get any lower than that based on classical arguments or semi-classical arguments. And now you're showing that there is a problem with the page time also. So would this be a problem in your view of constructions of the de Sitter vacuum and string theory, which predict that a lifetime much bigger than page time?
Yeah, I think so. So I think there's also, I mean, these sort of general arguments, I think they have appeared earlier also. So there's also a nice earlier work by Nima and some collaborators, where they really talked about the inflationary setup. So there the idea is that you're collecting basically information in flat space after inflation. And then you also find that there are inconsistencies if inflation lasts longer than at page time. So that seems very natural.
But yours is even shorter than that.
Yeah, so in this specific setup, indeed, so the difference is that here we're considering everything with respect to the static observer. So then we find a shorter timescale.
Okay, thank you.
Okay, good. I think there's one more question by Alec.
Hi, thank you so much for the really nice talk. So I have a conceptual connection between the, conceptual question about the connection between this scenario and what plays out in the black hole case. I might be missing something. So my understanding is that in the case of black hole, after we wait like one page time, the radiation on the outside of the black hole is like maximally entangled with the black hole, and because of that, the entanglement wedge like of the radiation gives you the island inside a black hole. And in De Sitter space, that's my understanding of the page time. And in De Sitter space time, if you start with a Bunch-Davis vacuum, it's already in a sense maximally entangled between the two causal diamonds in De Sitter space. So I'm just having a hard time understanding like what's the role of that process that gives you maximal entanglement, which is the like conceptual meaning behind the page time and in the case of like De Sitter space.
Mm-hmm. Yeah, so what happens in the black hole is I think if we just take Hawking radiation, then also for Hawking radiation, if the black hole is still young, let's say, then the modes of the Hawking radiation, they're still maximally entangled. It's only that you really have to wait up until the page time, until the subsystem that you have access to is big enough for you to reconstruct some information from that. And I think that is exactly the same in the Sitter space here. So, but indeed, so in the Sitter space, you already start out in the thermal field double state. So indeed, the patches of the north and the south pole, they're already maximally entangled. But still, it's true that if you now want to look at a subsystem, so I want to collect some radiation and put it in, let's say, a compact system, then that will be maximally entangled with a region beyond the horizon. But to reconstruct some information from that, I also still have to wait until that system is sufficiently large, which means that I would have to wait until the page time. And so it's actually kind of nice indeed, so from this island analysis, you can also deduce the scrambling time from a more quantum information sense, in the sense that how long after the page time does it take me to recover some information. And that you also see from this island that we found that also is the same formula as the one that Gary showed using this different analysis.
I see. But in the first part of the talk, like using the shockwave procedure, didn't you argue that after like one scrambling time in De Sitter space, you can recover information? So in a sense, when you start with a Bunch-Davis vacuum, you already are in the post like page transition phase. Maybe it's the role of the back reaction of the Bunch-Davis energy. I don't know, but I think I might be missing something, because it seems to me that when you start with the Bunch-Davis vacuum, you already have that kind of like post-transition maximal entanglement between the two like patches of De Sitter space. But maybe we can talk about it after like the workshop. But yeah, if you have anything else to comment on that, I would be happy to hear.
The
Yeah,
Scrambled
sure. I think
is the time scale after the black hole is already formed long enough to reach the page time, then information gets scrambled quickly.
Yeah, maybe to give just a quick answer, I think because I think the two, I think I understand what you mean. So I think the two things are not necessarily in conflict with each other. So because in the second part what we're doing, and that's sort of similar to the black hole, you're really talking about a complex system which has some Hilbert space, and you're doing measurements on that. And so that will take a page time before that system is large enough. Or sort of in the first picture where we use these shock waves, there you're allowed to basically act on the entire static patch. And then indeed, it's true that the entire static patch is all maximally entangled in the region beyond the horizon. And that it only takes a scrambling time to recover something using a shock wave.
Good. So maybe there's one more quick question with a quick answer possibly. Let me see. Arthur. So one more question by Arthur.
Yeah, very stupid, very naive. So if there is no curious observer, so if nobody is harvesting information, is there still an argument for the back reaction? I mean, does it happen also without anybody observing and affecting the black hole, affecting the sitter?
Yeah, so the quick answer is no.
Okay.
So I think you really need this observer to do something. Otherwise, I don't see how you would get the constraint.
Okay, so a stupid observer can live for a long time and be happy in the sitter. That's good to know.
Yeah.
Okay,
sorry.
so
Thank you. Thanks a lot. Yeah.
this was indeed a nice short question with a short answer. So I think we should proceed, and we thank Lars and Gary again.